Picture this: a storm slams into the coast. Waves hammer a jagged chunk of ancient pier. 2,000 years of salt and time are chewing at it like a buzzsaw. The camera moves close and you can see it. Not crumbling, not spalling, it looks tougher. As if the sea has sharpened it. Then cut to a modern bridge with rust stains bleeding through the concrete, chunks flaking off, traffic rerouted. Repair crews installing scaffolding before the structure hits its 50th birthday. How did we get here? How did the Romans pour stuff that laughs at oceans while ours throws a tantrum at road salt and winter? Let's peel this back with a simple promise. By the end of this story, you'll know exactly why Roman concrete lasts centuries, and why so much of ours struggles to make it past midlife without expensive therapy. You'll see the chemistry, the craftsmanship, the trade-offs, and the fixes we're starting to use, and you'll be able to walk past an old seawall or a new parking garage and call your shot on what will fail first. Start with a myth we need to retire. The Romans did not have a secret single ingredient that we lost. They didn't stumble on some magical powder, and then the recipe vanished like a library scroll. What they had was a whole system that fit their world. Different materials, different expectations, different designs. They built for mass and longevity, not for speed and rebar and budget cycles. The genius is in the combination and in the patience. Here is the Roman foundation. Their binder was lime, not modern Portland cement. They heated limestone to make quicklime, then slaked it with water, then blended it with volcanic ash known as pozzolana. That ash is rich in reactive silica and alumina. When it meets lime and water, it forms long-lived minerals that knit the mix into stone. The Romans had access to some of the best ash on Earth around the Bay of Naples. Think of it as the perfect reactive filler. It didn't just bulk out the mix. It took part in the reaction and built durability molecule by molecule. Now look at where they put it. Roman builders poured that lime, pozzolan mortar around heavy aggregates and masonry. They did it in thick walls, stout foundations, and massive vaults. No steel cages sat inside those walls waiting to rust. No tight deadlines pushed them to strip forms in 2 days. Their concrete cured slowly. It gained strength over months and years. That slow growth mattered. It produced dense microstructures and stable minerals. You can see it in the Pantheon. That dome is the largest unreinforced concrete dome in the world. It has stood since Emperor Hadrian was taking meetings. It still sheds rain and carries tourists. If that weren't enough, look at the coastal works. Roman marine concrete didn't just survive the sea. It mined the sea for durability. Seawater brought in ions that reacted with the ash and lime. New crystals grew in the pores. The interface between aggregate and mortar healed and strengthened. Imagine a structure that becomes more cohesive as it ages. That is not science fiction. That is what their chemistry allowed. There is another detail that flips a light on this whole topic. Ancient Roman concrete often contains bright white flecks called lime clasts. For a long time, historians thought those were just sloppy mixing. They didn't stir it enough. Then recent research took a harder look. Those clasts were not mistakes. They were hot, unhydrated lime fragments that went into the mix on purpose. When cracks formed later, water seeped in, hit those reactive pockets, and triggered a tiny local reaction. The crack filled with new minerals. Self-healing, courtesy of a material that stayed hungry for water. All that from a cheaper, simpler binder that we often dismiss as old tech. You could say the Romans left time, release repair kits scattered through their walls. So why doesn't modern concrete behave like that? First, we use a different binder. Portland cement is made by heating limestone with clay until it forms clinker. Grind the clinker, add gypsum, and you get a powder that hydrates fast. Speed is our superpower. We can pour a bridge deck at dawn and drive trucks over it soon after. But the hydration products with Portland cement create a different microstructure than the Roman lime, pozzolan system. The result can be strong and stiff, but it is not automatically more durable, especially when steel is involved. And steel is the second key difference. Almost everything we build uses reinforcement. Steel lets us make thin slabs, tall buildings, and long spans. It carries tension that plain concrete cannot. The moment you add steel, you add a ticking clock. Concrete is alkaline, which protects the rebar with a passive film. But carbon dioxide from the air slowly lowers the pH, a process called carbonation. Chloride ions from deicing salts and seawater sneak in and break that protective film. Once the steel starts to rust, it expands, cracks the concrete from the inside, and invites more water and oxygen to the party. You have seen the result: rust stains that look like teardrops, flakes falling off. That is not the fault of concrete alone. It is the chemistry of steel inside a porous mineral that lives outdoors. Third, we push projects to be thin, fast, and cheap. Curing becomes an afterthought. Good curing keeps concrete moist and warm enough for hydration to continue. That builds a dense, durable matrix. Poor curing leaves a brittle, cracked skin on the surface, full of pathways for water and ions. If you have ever seen workers hose down a slab and then walk away, you get the idea. Not all projects skip curing, but enough do that we see the legacy everywhere. Fourth, our aggregates and cements vary. Alkali-silica reaction can pop up if certain reactive sands or gravels meet the alkalis in cement. It forms a gel that swells when wet. The concrete expands and cracks. Sulfate attack can hit when ground soils or water carry the wrong chemistry. Freeze, thaw damage can shred pores if a mix was not designed with the right air content. Modern standards try to control all of this, but the real world is messy. The Romans faced fewer of these specific land mines because their recipe and massing were different, and because they were not using steel that forced the whole scaffold of durability to be perfect every time. Before this sounds like a nostalgia tour, remember that our concrete can be extraordinary when we design for it. We build skyscrapers that shrug at the wind, dams the size of mountains, ultra-high performance mixes that you can cut with a knife only if you bring a diamond saw. We can tailor properties in ways a Roman builder could not imagine. The problem is that a lot of everyday construction uses commodity mixes and rushed schedules. That is where the cracks show up first. So what made Roman concrete so sturdy at the microscopic level? Two phrases unlock it: pozzolanic reactions and long-term mineral evolution. The ash the Romans used was full of amorphous silica and alumina. Mixed with lime and water, it formed calcium, aluminum, silicate hydrates that are stable and dense. Over time, especially in marine environments, those hydrates morphed into even tougher minerals like aluminous tabermorite and philipsite. These crystal needles stitch the matrix together. In modern concrete you see a different balance. You get calcium silicate hydrate as the main glue and a lot of calcium hydroxide that can leach out. The Roman mix consumes most of that free lime into additional binder. Fewer weak links, fewer leachable products, tighter pores. It is like upgrading the stitching on a jacket from cotton thread to Kevlar, while also shrinking the weave. There is also the way they matched the mix to the job. Roman harbor works used coarse volcanic aggregates and ash that reacted well with seawater. Vaults and domes used lighter pumice higher up to reduce weight. They understood grading, density, and the way loads flowed. You can walk through the ruins and see the layers. Heavy at the base, lighter mixes near the crown. Material science by intuition and trial. The results still stand. Now the obvious question: can we do this today? Absolutely. In fact, we already are. The fastest path is to borrow the Roman trick of adding pozzolans. Many modern concretes already include fly ash, slag, natural pozzolans, or calcined clay. These materials reduce the amount of Portland cement, cut carbon emissions, and improve durability. They consume calcium hydroxide and fill pores, just like the Roman ash did. There is a slow shift in building codes from simple, minimum cement content rules toward performance specifications. That lets engineers design mixes for low permeability, high resistance to chloride ingress, and longer service life. When you set the target as, keep salt out of the rebar zone for 75 years, you start seeing mixes that behave more like the old stuff. We can also take steel out of the equation where it makes sense. Fiber reinforcement can reduce crack widths. Basalt or